Okay, good afternoon. Sorry about the delay. I don't know what happened. My laptop suddenly got frozen and I was trying to click and click. It didn't work and it just got turned off by itself. That was weird. That was the first time this happened to me. But anyhow, today and tomorrow you're going to have your first midterm exam. And again, I hope you studied hard. It's a little bit more challenging than the first midterm exam. And good luck to all of you. And I just want to mention that your grades are going to be in either Saturday night or by Sunday morning. And the reason I'm doing this, I asked the GEs to post the grades there because Sunday is the last day that you have a choice of changing your grade, either to pass, no pass, or graded option, or withdrawal, or whatever. So at that point on Sunday, probably you have almost 69, 65, 70% of your grade. You can make a, good decision what do you want to do with that, getting that grade. So whatever your grade is, that means if you stay in that path, give it or take, you're going to lose, I don't know, a few percentage. And if you do well, you're going to go higher. If you slack off, you're going to do, whatever you got, lower than that. But if you're doing whatever you're doing, that's going to be on the average your grade. Okay. Other than that, if you don't have any questions, I can continue lecturing on. No questions? All right. So if you recall that we are talking about inference, this was about inference about population mean. In this population, when we are talking about population mean, we assume that sigma is unknown. And that is the reason we learned that instead of having z distribution, we are having t distribution. With the t distribution, almost everything is the same, except the t distribution has degrees of freedom. And also, when you look at the curves between those two, you can see that the t distribution is a little bit kind of chubby, fat. So it's lifted up a little bit, and you can see the tail parts are compared to this one. This, if you want to calculate the 5% here, this goes all the way to long way to the right and long way to the left because it's narrow, because it has to cover that 5%. But this part, it just cuts out here at this point, and this represents 5%. And we went through the entire thing, and if we wanted to calculate that, we said since we don't have sigma, we have to calculate standard deviation for the sample and use this one as sigma. And then we did this. And this was the transformation in the z domain. We did this one. In the t, we did this one. It's similar. You can see that x bar, mu, mu. Sigma becomes s, and the rest is the same. The only difference, again, was the degrees of freedom in the t distribution. And again, I compare the t distribution with the z distribution. The black pen drawing here, it's the z distribution, and red and green are a t distribution. Within the t distribution, we can see that if it gets lower and fatter here, so therefore the degrees of freedom is lower. If you increase the degrees of freedom to 9, you can see that this is approaching to the z curve, z distribution. And if 9 goes to infinity, this becomes exactly like a z distribution. These were the confidence interval formula that we can use this for the level that we use it. In the z, we use x bar plus or minus z star sigma over square root of n. Here, instead of z star, we are going to use t star. Instead of using sigma, we are going to use s. And I showed you how to find the t star value on C table. You look at the column here. This is degrees of freedom. You look at the row here, this is the confidence level. You just, for the degrees of freedom, you just go on this row and drop down from this column, and that's going to be the T star. And T star, you use this T star in the formula up here. and calculate confidence interval, which is this one. What else do I want to say here? That's good. And again, to remind you that degrees of freedom is always one less than the sample size. If the sample size is 10, degrees of freedom is 9. You subtract 1 from that, and you do the normal calculation. And then we talked about the robustness. So we said that if the sample size is less than 15, so definitely you need to have a almost close to normal distribution. You want to have almost symmetric and no outliers and so forth and so on. But if the size is between 40 and 15, you can relax on some of these, like you can have at the most slight or moderate skewness. That's okay as long as sample size are between these two numbers. And if the sample size is greater than or equal to 40, then any distribution you can use as a t-test. All right, this was the example on lightning, I think, the current, and we calculated this, and we went through this. Basically, that's an example. The 90% confidence interval, was it 90%? What was the percentage on this? Yes, 90% confidence interval. And we calculated the conditions for this. What is it says, so we know that why should we be concerned about the validity of our significance test? Because the size is small. And remember that we had for robustness, we want to have n less than 15. That means it has to be in this range. And if you want to have in that range, so you need to have the curve to be really, more close to symmetric and no skewness. That was a quick review on t-distribution. And as again, when we say sigma is known, that becomes more realistic. Previously on the z-distribution, you don't know sigma. You assume that you know the sigma from previous observations that you had years ago, and you come up with something with calculation and sampling and all those things, and you say this is a sigma of population. But in reality, you can't get the sigma of population, because if the population is large, calculating standard deviation, it's going to be a headache. So for that reason, we use t-distribution. We assume that we don't know sigma. We take samples, and the sample standard deviation divided by square root of size of the sample, that represents basically the sigma part. All right, let's go with this example 4. Evaluate the hypothesis that alcohol increases the time before responding to stimuli. Subjects are given a moderate quantity of alcohol and then instructed to click a button after seeing a particular image. The average response rate for the population of sober individuals is 220 milliseconds. And well, this 220, that would be mu, right? So this is average for response for population. So that would be mu. We'll talk about this at this point. Do we need mu? Yeah, let's write mu. Mu is 220 milliseconds. And for a particular motor skill test, on the same motor skill test, you have SRS of 50, N is 50. It's SRS, and SRS 50 subjects provides a mean response rate of 226. So that means X bar is 226. And with the standard deviation of 16.5, so that is the standard deviation of the sample, and that would be 16.5. So these are milliseconds, right? So we are looking at the response time, and that's 220. Okay, so before I continue there, I mentioned that in Excel, you can use, like, remember we use norm.dist for Z distribution, here using t.dist. So in this case, your X would be, if you're using X bar, this would be X bar. degrees of freedom, that would be the size minus 1, that would be 49 here, and you put 1 there. And for TIMV, I think you get, I gotta put it on that thing, let me see. Do I have it here? TIMV formula. Yes, TIMV is giving, it's gonna give you probability and degrees of freedom. So for this one, so probability is 99%.99. Degrees of freedom, whatever the degrees of freedom is, you put that value there, and when you enter that value, it's going to give you the t value. Remember, we had the same thing with the z distribution. In the z distribution, we said norm.dist or norm.s.dist. You got the probability, and if you wanted to get the z star, we said norm.im or norm.s.im, and you put the probability there, you got the z or z star. It's the same thing, the same formula with different names. And the only difference here is you're using degrees of freedom here. For the test distribution, you use degrees of freedom, but in the z distribution, you don't have degrees of freedom. So those are the things that you use in Excel. Okay, let's move on this one. So from here, I know my degrees of freedom has to be 50 minus 1, and that would be 49. Okay, I have degrees of freedom. Now let's write the test, and the test would be H0. H0 is mu has to be equal to mu 0. Whatever the norm is, we are going to take that one as, or we are not going to have any influence on that. We are assuming that is the correct one. Always we assume that the null hypothesis is the correct answer, or true answer, so to speak. And then we design the test H sub A to contradict this one if we can get the right p-value. So mu equal to mu 0, that means my mu 0, yeah, this is mu 0, right, 220. So therefore, I can say H is going to be 220, mu 0. And that's millisecond. H sub A, because it says here, increase. It says the alcohol hypothesis, evaluate the hypothesis that alcohol increases the time response in the stimuli, right? So that means, for that reason, my mu has to be greater than mu 0, or we say mu has to be greater than 220 milliseconds. That's based on this increase over here, the word increase that we have. Now let's see, the idea is we want to find the p-value to validate or to say that our alternative is correct, but the null is wrong, or vice versa. That's what we have to do. So in order to do that, so I need to know, like the way we did it previously. In the previous chapters, we had to calculate z and look at the table. Here we have to calculate t and look at the table, including with the degrees of freedom. That's what I'm going to do. T is equal to x bar minus mu divided by s square root of n. I'm going to write z on this side. Here we had z equal to x bar minus mu over sigma. See the difference here? This is s over square root of n, and here we put mu, this becomes t. Let's put the values here. X bar is what? X bar is 226 minus mu is mu 0, which is 220, divided by S is 16.5, divided by square root of 50. That's the sample size. Let's look at the Z, but we're working on t-bar. Okay, so now let's move on. So t is equal to, if we calculate this, it's approximately, it is 2.5713. Again, remember I use this one mu greater than mu 0. Why? Because TR, when you drink alcohol, the response time is greater than T of sober time, when you don't drink alcohol. So that is the reason this mu became greater than mu 0. If the question was it decreases, this would have been decreased, less than. If the question was there is a difference, and we don't know whether it's increased or decreased, this would have been not equal, okay? Here right now, it's greater than, therefore this would be greater than, mu greater than mu 0. All right, so what do we have? Now we got to find, we have T, that's T value, and we have DF. DF is 49. So we are going to grab that C table. So we are going to look at on the C table. Rho is going to be 49. Okay. When you look at rho, you go, what do you have here? You have between 40 and 50. There is no 49 here. You see that? So you always go you go to the row that is less than 49. You don't go above 49. If I have 49 here, I don't pick 50 because it's closer. I'd rather pick the one below that. That means 40. 40 would be my row for 49. Even this is 49.99. I'm just giving you an example. It's not. It's in terms of it has to be whole number. But I'm just saying that if you have any number as close as to 50, you always pick one below that, not above that number that you're looking for. Good, you have it. In this case, our number over here is 49. Since we don't have a row for 49, one below that would be 40. I'm going to look into 40. So that would be 40. That would be my row. And then in this row, I'm going to look at the T. T was what? We calculated T is 2.5713. So we are going to look at for 2.573. It's going to be in between. See that? It's in between 2.57, 2.57. It's going to 713 lies between these two numbers. Okay. So what happens, and just remember, I'm going to put this number, put this one here. Now, when you look at down here, since you have mu greater than mu 0, it's one-sided, right? It's one-sided. I'm going to look at the p-value, which is going to be one-sided p-value. And that p-value is going to lie, if you draw a line from here all the way down here on one-sided, it's going to lie between 0.01 and 0.005. Right? You guys got it? Okay. So what I'm going to do, I'm going to draw something here, and you can see what I did. So this is my DF, and DF is going down. So you have 40 here. The next is 50. Then what is the next one? The next one is 60. All the way goes to 1,000. And then here, down here, you have two rows. One is called one-sided P, and the other one is two-sided P. Again, for two-sided P, you want to have mu not equal to mu 0. Use this one, right? For one-sided, either mu has to be greater than mu 0 or mu has to be less than mu 0, or can't have both. Okay. In our case, is this one. Mu is greater than mu 0. Therefore, I'm going to look at one-sided and not two-sided. Okay. Now, here we said our number, our DF was 49. But we can't go for 50. We have to go one below that, and one below that, the row is 40. So I'm going to look at this row, 40. And then I'm going to look at the number, what was it? Here, this T value here. So I'm looking this T value, this is along this line, row. I'm looking for T value, and T value is not going to be exactly the same. It's going to lie between two numbers. In this case, 40, that would be 240, that would be here. That's going to be 2.423, and this is going to be the next, it's going to be 2.704. Okay. All right. So we have this. We got this value for t. Those two are the two values. And here lies my t value. T value is 2.5713. You can see that it's between those two values. So now I'm going to do on the table, I'm going to drop a line all the way to single-sided, one-sided p. And that would be here, this row. Look at this line. I see that to the right of this line, this is that line. See that? This is that line, and this is to the right of this is 0.005. To the left of this is 0.01. Okay, so those are the two values. So my p value is going to lie between those two values. That's it. So that's how we are going to do it. So I'm going to write here p value lies between these two values. That would be it's less than 0.01 or greater than 0.005. Notice that you don't put 0.01 here because that mathematically doesn't make sense. Always when you say something less than greater number and greater than less smaller number. So you write it in reverse order. That is the p-value. So if you convert this to the percentage, that means in terms of the percentage, this is like between 1% and 0.5%. This is definitely way, way smaller than 5%. So from here, we say we reject the null hypothesis. We reject the H0. That means mu is greater than 220 milliseconds. So that means the response time when you drink alcohol definitely is slower. That means it takes a long time to respond. And that's why we concluded from here. Okay? It's really straightforward. You can actually use part of this argument towards your second midterm exam. Okay. Are we okay with this problem? Questions? No questions? Okay. All right. This is now. This is. Are you guys there or no? I just want to make sure that someone says just respond, yes or no. Oh, good. It's so quiet, so I thought maybe no one is there or something is happening. Okay, let's move on to the second problem. Good, thank you. Let's move on to the second problem. And the second problem is going to be this one. It says makers of generic drugs must show that they do not differ. They do not differ. Remember, this do not differ means that if you want to work this one with use null hypothesis and alternative, that means it's not equal, not greater than or less than. No, they do not differ significantly from the reference drugs that they imitate. One aspect in which drugs might differ is their extent of absorption in the blood. Below is data taken from 20 healthy, non-smoking male subjects for one pair of drugs. Number 1 to 20 were assigned at random to the subjects. Subject 1 to 10 received generic drug first, and subjects 11 to 20 received the reference drug later. First. Okay. Carefully explain why this is a matched pair design. So first of all, let's look at this number. These are the subjects we have. That means 20 men. So remember how we can randomize people? We give them a number, and you give them, okay, you're going to be number 1, 2, 3, all the way to 20. And then randomly, you can give them randomly number. You can take the names and randomly give the numbers if you wanted to do it that way. So make it completely random. Or you can say the subject one is we're gonna give him this, it's gonna be first, second, and randomize again. You can use the B table, we had it before, or you can use Excel. Excel use random that you can use random actually. That the number between that gives you the number between like a 1 and 20, with 1 and 20, it gives you these randomized numbers. So the reference drug, the absorption rate is going to be on this one, that would go for reference, and this would be for the generic drug. Okay, so we have this. Now we are going to use these data and do this problem here. It says carefully explain why this is a matched pair. The reason for that, you can see that reference and generic drugs used for both sides, for both subjects. So you match two men, you give them first generic and then reference and vice versa. So you're matching those two. It's matched. It's perfectly. 10 of them are going to be, here, didn't we say that? Like here, we assigned at random to the subject. Subjects wanted 10 receive generic drugs, therefore the other 10 has to receive. You have to pair them up with these 10. The other 10 is going to receive the other drug first. And that's what we have. Therefore, we say this is a matched pairs design. Draw a histogram of the differences in absorption. Reference minus generic. So this would be reference, that would be generic. So I'm going to write down the difference here. By the way, this is going to be one of your Excel problems. Exactly word by word, it's going to be Excel problems. So if you know the solution to this, all you need to do, you can actually check your solution against this one, but you have to use Excel functions. Now you can, here we are using the table and using calculator and doing the calculation. In Excel, you have to use Excel functions and do this. When I say exactly, I'm talking about the procedure is the same. Numbers are going to be a little bit different because Excel is more accurate than the tables. So anyhow, so what we are going to have, we are looking at the difference. It says reference minus generic. I'm going to put reference minus generic on this part. So we are going to write these numbers. I calculated this just a while ago. So we have 2353. Remember, you take the reference, you subtract from reference the G value. And the next one is going to be 1388. Next one is going to be 116. But these numbers should be exactly the same. If you use Excel, you can use Excel, right? Remember, you can go to next. You have these two columns in Excel. Go to the next column. In the first column, say click reference, write equal, click this one, minus click that one, and then grab that end of the cell on the right side, lower right end of the cell, and grab it all the way down. It populates all the cells, and it shows a difference. And those differences, that's how I did. I calculate. When I say I calculated, that means I got it from Excel. The next one is going to be this one. That would be 523. That would be 343. And this would be 298. That would be minus 169. Pay attention. Yeah, this is smaller than that. It's going to be negative number. And then you have 147. And then you have minus 19 and minus 394 minus 438. And then you have minus 262 minus 796 minus 349 minus 591 minus 702 minus 1111 minus 1650 minus 2030. We got all those numbers written. Now, if I want to plot the generic, and it says the class size or the width of each column on histogram should be 500 units. Can you move the paper into the frame, please? Can't see. Okay. Can you see it now? Okay. So now we are going to use this in order to use that. So I can look at my min. This is going to be my min, right? It's a negative 23. I think that's the lowest I have. Do I have anything lower than that? No. And this is going to be my max. That's going to be higher than that. So if I want to plot this, so I have to start with my bit, since my class size is 200 to 500, so I can start from minus 2500. Draw this. I can start from minus 2500. That would be minus 2000. Then that would be minus 1500. This is could be a good practice for your test too. Minus 1000. Minus 500. 0. 500. 1000. 1500. 22,000 and 2,500. So I covered all my bases. You can see that my min is 20 minus 2030, so it's going to be somewhere here, and my max is 2353. It's going to be somewhere there. So I covered it all. So the next thing I have to do, I have to just count again. Remember, in Excel, in histogram, you include 2,500, but you don't include minus 2,000. Up to minus 2,000. So you're going to count these. You're just going to look at the difference here. See how many numbers do you have between minus 2,500 and minus 2,000. Minus 2,500, you have one here, and all the way up to minus 2,000. Do you have any other one? No, you don't. So you're going to go 1. This is going to be 1 unit. The next one is, now you include minus 2,000 all the way to minus 1,500, not including minus 1,500. Do we have another one there? So that would be, we're going from minus 2,000 to, do we have one? We don't have one? Minus 2,000 to 15, oh, it's here. Minus 1,650. Okay. Sorry, I get bogged down with just doing this. Okay, so we have minus 1,650 here, and that's only 1, so that would be another 1. From minus 1,500 to 1,000, minus 1,500 to 1,000, that would be 1. I don't think we have anyone up here. No. So that would be another 1. From minus 1,000 to minus 500. Minus 1,000, that would be 1. This would be 2. And that would be 3. 3, 3, 3, 3, 3, 3. We have 3 of them. So that would be 1, 2, 3. This is 3. The next one is between minus 500 and 0, minus 500 and 0, minus 500 and 0. So that would be 1, 2, 3, 4, minus 500, 4, 5, 6. The rest of them are positive. We don't have a, so we have 6 of them. Goes all the way. So that would be 6. Between 0 and 500, 0 and 500, 0 and 500, that would be 1. 0 and 5, 2, 3. Right? 1, 2, 3, 4. I have 4 of them, right? Did I do it wrong? 1, 2, 1, 2, 3, 4. Fine. And then I have between 500 and 1,000. 500 and 1,000. That would be 1. That would be 1. I don't have 1,000 there, right? Between 1,000 and 1,500. 1,000 and 1,500. I don't have anything, do I? No, I have 1 here. 1,000 and 1,500. That would be another 1. Between 1,500 and 2,000. 1,500 and 2,000. This would be 1. There's no 2,000. That would be another 1. Between 2,000 and 1,500, we don't have any. Yes, 2,000. I hope I'm doing the right thing. And between that and that, you have only 1. So you have to have 20 all in all. Do I have 20? 1, 2, 3, 4, 8, 14, 17, and 20. So we have 20 data points there. So when you look at this curve, basically, it is kind of, you can see that the symmetry almost symmetric. You can see that this side and that side, it's almost symmetric. So we drew this histogram. It says draw this. We did this. So now part C says, given what we know about the data, can we accurately perform the t-test? Remember, if you want to have t-test, you have to have SRS, you have to have n to be some limited number, right, around 15, skewness, symmetric, and so forth and so on. So here we know that this is SRS because it says that it's randomly they pick, right? Here it says assign at random, so it's SRS. What is the size of the test? N is equal to 20. We pick 20, then we split it to 2 tens. Is it? It looks normal. Not exactly, but it looks kind of normal. So we can say normal distribution. And it is almost symmetric. Also, there is no skewness, right? No. Do we have an outlier? No outlier. So we have this, we have that. So we can conclude that yes, we can perform t-test. Okay. All right. We are okay. Let's move on to the next page. All right, in this page, let's look at the do the drugs differ significantly in absorption? So let's write the null hypothesis. Again, remember when we want to write null hypothesis, we are saying that H0 is defined to be mu is equal to mu 0. But we are looking at, if you look at here, we are looking at the difference. So instead of writing it like this, since we're looking at difference, basically the question is, we want to say mu reference is the same as mu generic. Or we can use this one H0, since we are looking at the difference, we say mu reference minus mu generic, it has to be equal to 0. Or there's another one, we say H0 must be equal to mu 0 is equal to 0. So you look at this one as a difference. You can write it like this, you can write it like this, you can write it like this, you can write it what I wrote previously. As long as you know what you're doing. Here you know that the mu 0 is the difference between reference and generic drugs. Here you just wrote those two and you said different. Here you're saying both are the same. All these thing I wrote here, they mean the same thing. Okay. In the case of alternative hypothesis, so I can say, if I want to go with this, I'm going to say mu r is not the same as mu generic, mu reference. Or if I want to use this one, I'm going to say mu r reference, if you find subtract mu g generic is not equal to 0. That works too. Or you can say H0, in this case, mu 0 is greater than, not equal to 0, I'm sorry, not equal to 0. All these are the same thing that you're doing. Okay. If you have read the textbook or if you have paid attention, I'm going to give you a good hint in this lecture. Might be useful. When we write the null hypothesis and alternative hypothesis, can I put here X bar instead of mu bar? Mu. Can I do that? No, I can't. Because this is specifically designed, H naught and H sub A, both of them are designed for population. So you cannot use, say, X bar of reference is equal to X bar of generic. The minute you see X bar in any of these things here, then you know that's wrong. All right. Okay, let's move on. Let's find out, what is it? To find the p-value, I'm going to write it. Again, it's a similar thing that we did with the z. We are going to go exactly the same. We're going to take the same route. So to find a p-value, so for t-test. So what are we going to do? So first we are going to find the t value. T value is equal to, you have X bar minus mu divided by S divided by square root of n. N is 20, we know that. So therefore, df, degrees of freedom, would be 20 minus 1, that's 11, 19, whoa, 11. You subtract 1 from 20, that's 19, not 11. All right. Okay, now we have the mu. This is that mu 0, the difference we're looking at it. Anything else we need to know? Okay, so we need to find the standard deviation. So in Excel is much easier. When you write this, you can just say standard deviation S, that means sample, just prints out that standard deviation, that's what I did previously prior to this. So standard deviation, when I did that, it came out to be 1070.2, 62, I'm sorry, 62. Also, you need to know what X bar is. Again, in Excel, it's much easier to just click here and put equal average. That's going to give you the mean. Calculate that. And I did that too using Excel. X bar is minus 37. Okay. Now, let's put it in the equation. T is equal to X bar is minus 37 minus mu 0, this is mu 0, and mu 0, the assumption is 0. Remember, we assume that the null hypothesis is true. We want to know with our alternative hypothesis that we have here, alternative hypothesis, whether we can reject that or fail to reject. So that's going to be mu 0 here. S is 10, 7, 0.62 divided by square root of 20. And if you do this, you come up with approximately a number is minus 0.1546. In Excel, you could have used standardized, again, you could use this formula, but you have X bar because you calculated on that column. You have S, you have N, you have mu 0, everything is there. All you have to do, click that, put it in the parentheses, divided by, click on S, divided by on square root, type square root, click of N, put it in parentheses, you're gonna get the answer. Or you can use the function standardized that you use it for Z, when it had the Z value. So this is gonna give you this T value here. So you put the values there, X, mu, S over square root of N, and whatever there is, if there's 1 there, or a cumulative, you've got to put 1 there or true, and you get the answer. It's going to give you exactly the same as this one. If I get a chance, we'll go, maybe if I finish this, we'll go to Excel and do some of these functions. So, in table C, you don't have negative T. So you need to, we're going to look at T as positive. We're going to look at the absolute value of minus 0.1546, and that would be 0.1546. So that's going to be our T value, okay? That would be our T value. So in order to do that, so I'm going to show you on the table once, and then I'll go ahead and draw this again. So what is our degrees of freedom is 19. I'm going to put this one on 19. Row 19, you can see that. Degrees of freedom. Again, this is the degrees of freedom. 19, that would be here. And then I'm going to look at this row. What was the T? T value was 0.1549. Do I have 0.1549 here? You go all the way there. The smallest number that you see here, it's 0.688. That means 0.15 is somewhere to the left, extreme left of this point. Do you see that? It's not even on the table. So that means you can easily say that your p-value is going to be even to the left of this p-value. Okay? So if I look at the p-value on this, and since do I look at double-sided or single-sided? I'm going to look at it in double-sided. Why? Because mu is not equal to 0. So if I look at that one, that gives you 0.50 p-value. but we know that this is for what was it? 0.688. So if you do this for 0.1546, that means it's going to be even much greater than this number here. So I can easily say that my p-value is going to be greater than 0.50, and therefore, or you can say greater than 50%. This is way beyond 5% that we are interested in. So basically, having this, we can say failed to reject the null hypothesis H Therefore, mu equal to 0 is the right answer, and this means that no difference between reference drug, and generic drug. There's no difference between them. This is completely, it says we reject it. Okay, what do we have here? Okay, so far both examples, oh, let's see, let me go back here a little bit. So far, both examples that we have done, we haven't found an exact p-value, only a range of where the p-value falls in relation to the values that are in table C. Will that be common? Yes, that will be common in the problems that we do in tutorial and an exam. Or will we be responsible for finding out? No, it's not. That's something that you're going to see it. A lot of times. Even with the Z, if you can't find this, write that, you can do it the same thing. Next question is, where is next question? Could you explain how you found X bar again? Oh, X bar is here. So our X bar is we're trying to find the difference. We found the difference. So average of all these numbers. Average of all these numbers, add them up, divided by 20, that would be the average. Just don't forget to put in a negative number, negative signs there. Or you can use Excel. Excel use equal to. In Excel, you write equal average, and then click on the first one. Say that's going to be A1, colon, grab it all the way down. That would be A20, and enter, and this is going to give you minus 37. All right, good questions. Do you guys want me to draw the DF and everything that I mentioned here to have it in? Do you want to see that, or you're okay with the explanation, or do you want me to draw it? Why we couldn't find that 1.546, we had to go to the left. Are we okay with this, or do you want me to draw it? Yes or no? Quickly. Yes, okay. Let's do it then. So what we had here, we had DF, and DF is going down, and here we had our DF was 19. So we have this 19, and we do have 19. We do have this number 19 here, so we are okay with that. We picked that one. If we didn't have that number, we should have gone the one below that. Remember that, that's important. And also we went down, all the way down here, we are going to look at two-sided P. Two-sided P. And the reason for that, because of this. It's not equal, it's not equal, it's not equal, and therefore it would be two-sided. So we're going to look at the values in two-sided. And if you look at these values in two-sided, so the first one is 0.50, next one is 0.40, 0.30, and so forth and so on. That is a two-sided. I just wrote a few of them. So what we looked at it then, we said that we are going to look at this row. And if you look at that row, I'm going to write few numbers here. Then you can see when you refer to the table, you see what's going on. So on 19, we had 0.688, and the next one for 0.04 was 0.84, and the next one for 0.03, it was 0.1066, and I'm going to say the last one we have on the, if you check your table, you're going to see these things. And the last one over here, and this represents the last one, and the last one was 3.883. 3.883. Okay, this is the row for degrees of freedom is 19. So since you look at it here, you want to see this number there. This is your t value. You have to find a value between these here, and you can see that this is increasing. When you move to the right, it's increasing. So there is no way you can find anything to the right of this. So the smallest number in this row is this, and that corresponds to 0.50. So if this is the smallest one, therefore my 0.05, it would be way on this side here, 0.1546. And if you look at the p-value for that, this would be way smaller than that. I think once I used it, Excel, it's like 0.75. I'm not sure, I don't remember exactly. But if you use that, you can see that it is way bigger than this, because if you're moving to the left, your probability is increasing to the left. So therefore, that probability that corresponds to the 0.1546 is much bigger than this probability. And therefore, based on that, I wrote here p-value is greater than 0.5 or greater than 50%, and that is not good for rejecting the null hypothesis. We say we failed to reject the null hypothesis because 50% is, I mean, this is greater than 50%, even, way greater than 5%. Therefore, failed to reject. All right, questions? No questions? Okay, if you don't have questions, we are done with this chapter. So we should move on to the next chapter. What time is it? Oh, we still have 15 minutes. Or I'm thinking, should I go on Excel and show you a few things there, or you're okay with that? Or do you want me to start a new chapter? Yes, what? New chapter or Excel? Okay, let's do Excel then. Just remember, it's going to take some time to go to Excel, and I can't answer your questions on Excel, but I'm going to show you how to use TINV and so forth and so on. And just remember, if I refer to, we had some examples here, right? You can hear me when I'm there, but you can't see me you can see only on Excel. Just remember, when I refer to this example here, 99.5%. Now we had some examples here. I might refer to these and show you that we are getting exactly or similar numbers, so you can see that it works. Or we have another example, number 2 here, okay? Or another one here. All these examples. So just be aware that when I come back here and look at these things, I'm gonna do some of these calculations on Excel to see that you can do it there. All right? So I'm going to go to Excel now. Working. I'll wait for JavaScript. All right, run. Okay. Now you should be able to see it, right? I hope that you see it. I can. Oh, I can read. Can you see it now? Can you guys see it? I want to see that. If you can type, I can see something there. Can you type something? Oh, I can see you guys there too. All right. I can answer your questions. Okay, that sounds good. So let's just open Excel. I'm going to make the Excel smaller in case if you have questions, I can answer your questions. That's great. Come on. Okay, there we are. Okay, I'm going to make this smaller so I can see your question, and I'm going to make the cells bigger. See what we are doing. So are we okay with this? Can you guys see the Excel? Yes, no? One person said yes. Yes? Okay, good. All right. So if you recall that I mentioned that we have like a T-inv and T distribution, dot distribution. So we're going to go through some of those values and see if we get the right answer. So if you look at problem, let me see if I find one problem here. Which one was it? That 125. Yeah, I have it. Okay. There's a problem that here what we have. It says on page 2, problem that we did an L-level confidence interval for mu, right? And the confidence interval was 99.5%, and the T-star we calculated from table. T-star was 3.495. Okay, you have that. You can see that, right? So if I want to get that, sorry. If I want to get that T-star, I got to use T-inv. Okay, I'm going to use T.inv to calculate this. But before I calculate this, if you recall that we did the same thing with the Z, inverse of Z. When we wanted to calculate, we had the probability, then we calculated Z star. If you remember that, when it says 99.5% of the curve area, so that means you have two tails on the side of that 99.5%. And each tail is 0.25%, right? 1 minus 99.5, you get 0.5. And if you divide that 0.5 by 2, you get 0.25 for each tail. Okay, are we okay with that? So 1.25 of 2.25 would be to the left of the 99.5%, and there is another 0.25% would be to the right of the area 99.5%. So if I want to calculate, so if this is the area given to me, and I want to find what the T star is, I'm going to say T star, so it's going to be equal. On this side, I'm going to write the equal sign, and I'm going to say T dot inv. So you can see that T dot inv here. Click on that, and it says probability and degrees of freedom. So probability for that, I'm going to pick. If I pick the left 0.25%, that's going to be on the negative side. I'm going to get negative T star, right? Can you envision what I'm saying? Exactly. We went through this on 2 lectures ago for the Z star. So if you go with that one, if you put the probability on the left tail, and the left tail was what? If you recall that, it is 0.5 divided by 2. That means 0.25%. 0.25% is, if you want to write it in decimal points, it would be 0.0025. Are we okay with that? Someone says yes or no, so otherwise I will explain it more. Do you know what I'm talking about? Yes, no? Yes, thank you. Okay, so that would be 0.0025. That is the left tail. And the degrees of freedom, if you look at that problem, it says 11. Notice that if I enter this is going to give me a negative T star because this is to the left of the center. So in order to not to have negative, I'm going to enter this. You're going to see that it's a negative number. So in order to get around this, I put abs here, ABS parentheses, go all the way here. That's absolute value, and enter, and that is the t value. If you look at your lecture notes, we calculated that was what? 3.497. This is exactly the same. I mean, not exactly, but it's the same number. That is with regards to t. You can also use the upper t value. Remember, if you want to use the upper one to the right one, so that would have been what? If you don't want to use absolute value, that would be, then you need to have what? You need to have 0.995. This is 99.5%. You got to add that tail to that to get to 0.205. So that would be 0.025. No, I put up an equal sign. So you can do this without t.imb. You can use this one here, comma, and what is the degrees of freedom? What is the degrees of 11? You should get the same answer. There you are. This t star is due to the right tail, and then when you look at the right tail is 0.0025, but to the left of that it's the area, and that area is the area under the curve, which is 99.5%, and the little tail to the left of that, that would be 0.25%. If you add them, it becomes this, and you get that one. Either way, you can do it. It's the same thing that we did in Z. Okay. Now I'm going to do the reverse of this that you can see. Remember, we did this for 99.5%. So I want to reproduce. Suppose I have the t value. How do I get this this probability? So in order to get this probability, I'm going to type this. You're going to see what happens. Then I'm going to adjust it. So let me type this t dist. So when I do this, I'm going to click on this. When I click on that, it says x degrees of freedom cumulative. Remember, cumulative was 1. Degrees of freedom is 11. And what is x? Your x is t star now. Okay? So let's put the values here. I'm going to put that t star. Degrees of freedom is 11, and that is 1. This is not going to be the same thing that you expect, but I want to show you what you get here. You got this. This is not 99.5%, right? So in order to get this number, so you need to subtract that tail from that. This is giving the area to the left of 0.0025. So you need to subtract from this. You need to subtract 0.205. So another way of saying it, let me write the formula. If I want to write a more accurate formula for this, I can say I will write one here. See what I'm doing here? That's going to give you, now this is that area that I'm talking about. You get this area. Now if you go back and do the same thing and subtract this number from that, that's going to be, or you can say, what I can do, say 1 minus 2 times this value. You already calculated that value. Oh, there's a sign, equal sign. A little bit tired. Equal sign. So here, now you're going to multiply by that and enter it. And that becomes 99.5%. So again, go back here. This is 1 minus t dist. You see that? So we put this value, t star, in it. 11 was the degrees of freedom. 1 is always 1, cumulative. And when you do that, you get this tail, the value of a single tail. So if you multiply this by 2 and subtract it from 1 times this 2, and you get that 99.5%. Okay? Let's see. What else can we do here? We only have a few minutes left. That's it. I guess if you have questions, I can answer. Otherwise, we only have 3 minutes or 4 minutes left. I'm going to go back to lecture in case if you have questions, I can answer there. Or you have questions here, I can answer. Okay, I guess let's go back there then, if you don't have anything here. All right. Okay, so if you don't have questions, let's, well, we're not going to have enough time, but I'm just going to elaborate a little bit on chapter 21 and then do leave it for next week. And basically chapter 21, what we did in chapter 20, instead of having dealing with one mean, we are going to deal with two means, two populations. And then we are going to look at the values there. So you're going to have two sets of samples. You're going to have two standard deviation for samples. You're going to have two sample sizes. You're going to have population mean that may not be unknown. They're not unknown because you're going to use the t-test. So in general, we are going to work with the two sample problem where we have two different sets of quantitative data, and we got to make sure that those samples are SRS first of all, and use this. This is an example. We can use this example. You can see we have two groups from two different population. We draw this two groups. Each group, first group has mean of 3.2. Second group has mean of 2.8. And the standard deviation for first group is S1. Second group is still. And size are not necessarily the same. Size are different. And that's the reason you're going to see that the formula is going to get more complex here. You can see that. So you have to extend the formula to include both of them. Anyhow, this is going to be for next week. So we only have maybe three more chapters. I'm hoping that if I can finish this, maybe the week after next. So the last week is going to be, we can just work on problems. Maybe I can, review problems that you will have, but aside from the review problems during the lecture time, we can do more problems together. We'll see what happens. Hopefully we'll finish the whole thing by the end of the following, not the next week, but the following week. So we have a week for review. So right now, this is week 7. We are done, so we have 3 more weeks left. All right. Good luck on your final, on second midterm, folks. All right. Have a good day.